Well, hello friends. I'm here to making another video to explain just the basics of how to store a single bit of information, or a single bit of logical data. Uh, I'm a software engineer trying to do electrical engineering as a hobby, but I don't want to go full electrical engineering. So I don't want to know the formulas. I don't want to know to make complex calculations until it's necessary. I just want to play around like discrete components and such. Maybe eventually store 1 byte in a proper way, in a consistent way. Then 1 bit in a consistent way. Then go to a byte, and then go to a full CPU, and then that's what I'm gonna do out of concrete oh, out of discrete components. And well, that's a lifespan project, so do not expect tomorrow if I do not expect a new video tomorrow saying, "Hey, I have a whole computer here." No, it's not. That's not how it's gonna happen. I have been trying to look for data about this on the internet for weeks now. There's a lot of good data there, but a lot of academical data. Either you use discrete components and you have like an IC that just a chip that contains all the stuff you want, and then you just build a computer like clever people like Ben Iter did. But I wanted to play around. This is a hobby, right? I don't want just to compete against Intel or AMD or something like that in the realms of CPUs. No, I just want to show some components in breadboard and see them blinking and see LEDs blinking and such. Yeah, it's like the hardware equivalent of software, or what I do in software. So yeah, this specific video, so don't expect this to be a deep, profound explanation of how to store bits in computers. There is a lot of good information there if you want to the real the real guts of how to do this and how all of the maps and such. As I said, I just want to show components on a breadboard and make it work. Eventually make some calculations, but only when it's needed. Yeah, right. So yeah, storing 1 bit of data. Conceptually, I found a very interesting idea that if you have an ideal buffer device, so if it can just recall what it like, if it can just replicate its input to the output in a perfect way, then you just show its output into its input, and then yeah, you just store that data like magically. That's a concept from 200 years, almost 200 years ago, and by Munchausen or something like that. Forgot the name, but yeah, it's simple, it's brilliant, but it's just like in the realm of theory. It's not practical because you don't have this kind of perfect device. In real world, one of the things we mostly do is use a set reset latch. This is like a common thing you can find in ICs, and it's just a matter of you have the output. Maybe you may have other things like the complementary output or clocks and what's not. But the simplest case, you have the output. You set if you change the set, you set it. If you change the reset, you reset it. It's like, it cannot be like simpler than that. And this is conceptually, it can be implemented as long as you have like two close to ideal negative not gates, right? If you have so you get one not gate output shove into input into another one input, and then vice versa. That's essentially a set reset. So if you convention this to be the output, you can just put this to 0. You assert this as 1. If you put this one to 0 as the reset, this one will go to 0. So like, yeah, it's conceptually that's how a set reset works. There is more things. You need more than just like 2 magic gates, but it's definitely something you can do. For instance, with a 7404 like this, you'll not be able to see. Oh, maybe you can see the yes, like it's a classic 7404, and I don't want to show my oscilloscope here or any blinking lights, but this is essentially like VCC ground, just like the spread that datasheet asks, and then I just set the output of the first to the input to the second gate and vice versa. And that if I just get my ground and I just tap, oh, camera, sorry. And if I just tap either, I'm just setting or resetting. And if I can just add my probe in one of those to be my conventional output, and that's it. Like, so if you want to, for some reason, you have, let's say you're making your own Benitez based computer and you want to save with flip-flops or set resets, you can actually, if you know this kind of shenanigans, you can be creative about how you do your set reset latches. And of course, in my style, in my more mad science style, you can go deeper than that, and then you can actually go down to transistors level. So you can have, instead of two simple gates, you can actually use two discrete transistors to do the set reset. This works because if you just look into this to this side, you can notice, if you know how to make your own gates out of transistors. I think Benitez probably have a video on that as well. This is so this transistor and this resistor with this as a data point, you actually have a NOT gate, right? If you just show one here, then the transistor is supposed to ground, and this data is more closer to ground than to VCC. If you have a 0 here, then it's the opposite. The VCC stays more. The output stays more at the logical one than logical 0, and that's this half is essentially a NOT gate, and this other half is also NOT gate. And if you just cross the inputs and the outputs, then you have this, and you have a set reset latch. You can just, I did that experiment here, right? It's the same thing. Two transistors, two load resistors, the interconnected base and collectors, and this is a set reset latch. So you can, if I just get my probe, if I get my input, set it to ground, and then touch I probably have a short on this one, and I touch either, I'm setting or resetting, right? And I have, and by the way, obviously you have complementary outputs here, because if this one is 1, this one is 0, and vice versa, and same here, right? So as long as you know how to do a NOT gate, you can just do a set reset latch, no matter what type of logic you want. You can even go for as further. You can maybe replace the BJT transistors with BJT NPN transistors with a NMOS MOSFET, right? Or like a 27000 or 27000 or 27002. Same stuff. Like you have a what's called the resistance load logic. So again, like this half is a NOT gate, very similar to this one. It's essentially the same. It's virtually the same. It just works with on internally, like if the pixies and electrons and gate and fields and what's not, they are very different. But for dumb guys like me, it's just like the same. Like as long as you know the parameters of what to expect in the output, they are virtually the same. And this is what's called the resistive. This is a resistance load type of logic using MOSFETs. And you can go even crazier than that by just going as this and using what's called depletion mode MOSFETs. This gets annoying that's the one that I don't have. I'm on the theoretical part of life, because I think hobbyists don't go as further as this, but cheap designers do. And yikes, yeah, like that's where you can only find math instead of parts numbers and what's not. Like I could not find a single example of someone actually building this. And unfortunately, the depletion load, it's called depletion load not only because it works on the depletion, what's called the depletion range of the transistor, but it also requires a special type of transistor, right? This one probably can be the 27000 or any of your favorite any NMOS transistor that you can find on the on Mauser, Farnell, eBay, what's not. But the depletion mode requires some special, so that like they are built differently, like if different the size. It's in a nutshell, it's a different one. Like just like this one, it's different, and actually, it usually represented with a stronger line or something like that, right? But yeah, because they are internally they are different, and this only works if you have this different transistor, different type of transistor. I could not test it, and honestly, I think I found 2 models of this that I can buy as a discrete component. I'm having a hard time to find. I might find some SMT versions, but they are freaking expensive. Like this one, I can find the 23904. You can buy like 100 for $1 or something like that. This one you can kind of buy kind of similar, the 27,000. This one, the cheapest I could find so far was like 50 cents each. So no, that's too expensive for just playing around, especially because if I want to make 8 bits out of this, this is already a single latch costs €1, $1 or whatever. Like no, so no, sorry. And if you read enough about logic gates, you know that these composition. So if you want to have a depletion mode, every gate in a nutshell has a depletion transistor. So that gets very expensive very fast. And another one that I'm having issues trying is the CMOS version, right? This is actually the. Oh yeah, by the way, speaking of benefits and pros and cons. Well, those are the pros of those are just how simple they are to find components. Like it's not that it's kind of cheap to play around this. The big con is that it's resistive load. So when there is always one of the paths is always conducting, right? So if you have which means that if you have, for instance, I think. Yeah, then you do that's where you do the math. V equals IR, and then you can get the I equals to V over R, and then you can make the maths, and you see how you're gonna your project will consume a lot of energy just on standby, because you always have a resistive path consuming current. This one gets cooler because the depletion mode MOSFET conducts like in the order of micro amps, or even less. It's like a really high resistance, and yeah, it's able to just make this work, essentially consuming virtually nothing, right? And yeah, so this in theory this works. Like you just like any other one, you just ground either, and then this makes the other path start to conduct, and what's on, and etc. So yeah, back to the CMOS. The CMOS version is very interesting. It's called, by the way, it's obvious, but it's called CMOS because the C is for complementary, which means that you always have an N MOSFET and a P MOSFET. And that's the part that makes it hard as a hobbyist, because it's not as easy or cheap to find P MOSFETs, especially in these where are my transistors? So especially in this TO92 package, it's really hard, or any package that you can shove on a breadboard, right? They are really hard to find. I don't know what I'm gonna. I want to try. I want to play around this, but yeah, like I need to find a way to get my hands on P MOSFETs to actually play. And they are interesting because, okay, they are just two NOT gates. If you just look at them, look at each half of them. And yeah, they are by far the best one. They will be the best one of all of these, maybe except for the hard to find, probably expensive parts, because it doesn't really conduct. Like, it only conducts when the output is there is no load here, in a nutshell. So the NOT gate of a CMOS, there is no load. Either you have the input pulls either side. So the same, you can see that it's the same input. It's the same input, but then either the P conducts when it's zero, so it negates and then makes the output goes connects the output to high, or vice versa. If it's 1, then connects 0 to the output to ground. And well, due to this property, you just make it them one of the input go to the output, the input of one to the output of the other, and then it will only conduct energy depending on how you consume the Q, the output, right? And again, same property. In theory, you can just put either to 0 and then you can set or reset, right? Yeah, that's essentially what I learned from a lot of research, and I might do different segments on different circuits depending on how I go, because right now I have a set reset. I want to promote that to a D flip-flop or maybe a T flip-flop, because I need registers and shift registers and what's not. I kind of need those. But yeah, as a small addendum, since we're talking about 1-bit storing data, this is storing based on like this architecture, like the actually Munchausen, I would say, architecture. But you can also store using dynamic or RAM, essentially. What I didn't went further because so the RAM, it's not made for like 1 byte, you read 1 byte, and like it's made for X amount of bytes, like you read X amount of data in multi-bit data. It's made for so in a nutshell, if you get things like read and write lines, you have multiple bus lines and what's not. Like, I have seen 2 different types of DRAM, which are really cool if you think about them. Like, if you get your like quadruple X, DDX, DDRAM, and blah blah blah, and you understand how they work on the bits and bytes, on the even lower than bits and bytes. Like you have, in this case, you have a cap that actually stores the data. Then when you write, you connect this cap to the bus line, and then the cap stores a charge, like a minimum amount of charge to keep a consistent level. And then that's the principle behind both of them. This one contains a single transistor, this one contains 3 transistors, and the 3 transistors, so the 1 transistor, obviously cheaper because less components, fewer components, and then but it needs refresh, because then when you read back the data, you are actually transferring the load from the capacitor to the bus line, and that's why you need refresh in dynamic RAM. And with 3 transistors, you just add, essentially you have a read path and a write path and a write bus and a read bus. When you assert the read line, then the charge of the capacitor just activates this. So the read activates. This is a very like a very small version of an AND gate, right? So you can, if the read is on and then the cap has charge, then the bus line gets asserted as well. Like this is really cool for when you're design chips, because they can be like very well stacked on the so not stacked, they can be very compact on how you design, and repeatable patterns and such. You can see from the original lines here, it's very repeatable. I am not sure if I might try this eventually, but I'm not sure if this is a good design for like a CPU register. Yes, let's say a CPU register, like a 8-bit register. I want to store 8-bit of data. Is this a good design? I'm not sure, because like, I might try to see other people's design on registers, how they doing it with Wi-Fi Cs, and maybe this actually helps me. But there is a lot of variables here that can go wrong, and I am not willing to take this path until I actually know what I'm doing in terms of of the whole stuff. But yeah, that was my video. I hope like you enjoyed all of that. Like this is a very concise view of how to store 1-bit data in, using discrete components. But yeah, I hope you enjoyed it, and leave your like, comment, and comments if you like it. I'm open to suggestions. I'm open to good critiques. I will just shamelessly ignore bad critiques, right? If you just say, "Oh, you suck," I will just ignore you, right? I don't feed the trolls. Don't feed internet trolls. That's life lesson, kids. Yeah, and see you soon. Bye.